defined last time. So if you recall them, these are, so we are given say a vector space V over some field F, and then we are talking about subspaces of this vector space V over the same field F. That means you just have to check two conditions. One is W plus, that is equal to this is an abelian group. The same plus that makes V an abelian group makes also W an abelian group. And then W is closed under scalar multiplication by elements of it. So closure under scalar multiplication and the closure under the usual law, the group law of this application. This makes this as subspace. Alright, so we are now going to introduce one more concept, that is of a span. So suppose we are going to define in a moment what is meant by span. Suppose you have a finite set of vectors, we want to do Vn, say a finite ordered set, a finite ordered set. Span will be more general, but at first we begin with a finite ordered set, we want to do Vn, then take the set of all linear combinations of them. So the linear combinations of V1 to Vn. By this we mean all relations like this, C1, Cn, Vn, where C1 dot Cn are in okay. What is V1? Yeah, of course, these V1 to Vn are elements in V. So the given vector space. So you are having a finite set of vectors in V. Okay. And then by linear combination of them, we are, well, this is the set of all linear combinations actually. Sorry, I have already written down the definition of span, but just by one linear combination, we mean this, not for all, but for some C1, C2 to Cn in F. Okay. So this would be called this thing. An expression like this would be called a linear combination of V1, V2 to Vn. C1 to Cn would be elements in F. Okay. And now, if you take all the set of all such linear combinations, that makes the span of V1, V2 to Vn. So we define span of this set V1, V2 to Vn to be the set of all linear combinations V1, V1, Cn, Vn, such that the Ci's are in F. Okay, it's a pretty straightforward definition. What we mean by this, and
sir,
yeah,
can C1, C2 up to Cn they be all zero?
C1, C2 to Cn could be all zero. That is, zero is inside the span as well. So all we care is that these Ci's are in F. So in particular, if we call, and if we take S to be a set, and this ordered set, we want it to be Vn, then we can denote this by, and this would be denoted by just span S. Okay. Alright. Now, if you take S to be an arbitrary set, again by span of S will mean finite linear combinations of the elements of S of this form. For a general set is in V, by span of S would mean finite linear combinations. Finite means that you take finitely many elements out of S in one group, and you take the linear combination of them with the coefficients from field. So finite linear combinations of the elements now, why we define span just after the definition of subspace? Because given any arbitrary S, if we consider the span of that, it will be a subspace. Yeah? So the first claim is that if S is a subset of V is a vector space. Okay? So for us, V will stand for a vector space. I'm not writing it in bracket. Just remember that this is our vector space. That the one we started with. Then span of S is span of S is the smallest subspace of V that is containing S. Okay. So, at first let's write that it's a subspace of V. The rest of the assertion will be rather simple. So it's a subspace of V. Okay. And why?
Zero. We have to observe that zero vector will always be in the subspace.
Right. Yeah. Sure.
Setting all Ci to 0.
Right.
Then it's obviously closed.
It's obviously closed because we are taking all linear combinations, and linear combination of linear combination is again a linear combination, so it will be there. Yes.
Then all the others are satisfied.
So you have to figure out that this is true. That is it's an abelian group, and that it's an abelian group under addition, and that it is closed under scalar multiplication. So that is an abelian group, and what you would require. Suppose this is so. We take span to be finite linear combination of this kind, right? What is the additive inverse of this?
minus.
Exactly. All is negative. Minus C1, P1, minus C2, P2, etc. minus C and P. Now note that if C1 is an element of F, minus C1 is also an element of F, right?
Yes.
So this is still a linear combination. It's inside that. Inverse exists. Identity exists, as Falgun already mentioned, that if you put 0 everywhere, you get 0. Okay. So both inverse and inverse and identity exists, and the law of composition is also satisfied, because if you add two such things, if you take two arbitrary linear combinations like this, if you add them, you get another linear combination. Okay. And for a general set, you are taking a finite subset of it, taking linear combinations of that, adding them, you are getting another finite linear combination of the things. Okay. So it's still in the span. Abelian group is very finite. Now, this one is kind of trivial, right? You are taking such an element, you are multiplying it with some element of F, then what you are doing is that you are sending such a thing
Multiplying by C prime.
Exactly, you are replacing it by C prime. So take an element of A, element A of F, multiply all this, all this thing with A. So it will be AC1 V1 plus AC2 V2 AC and Vn, which, as you just said, you can write instead of ACI, you can write CI prime, CI dash. That's also, all these CI primes are, because F is closed under multiplication, so all these CI primes should be belonging to F. So we are still getting a linear combination. In other words, span of a set will satisfy both of these conditions. So it's a subspace. Is this clear to all of you? If not, please let me know. That is, span is a subspace. Okay. Yeah, sure. Again, which part? All right. So what we have to, please go with me. And suppose we want to prove this. Your name again? Fine. Okay. So fine. If we want to prove this, then how should we proceed?
We have to show that and fix the definition of
yes. So that both of these are satisfied, right? At first, you need it to be an abelian group. For what do we need for an abelian group? At first, you need the law of combination, right? So if you have such a linear combination, a finite linear combination, and if you add a finite linear combinations of the elements of S with that, you get another finite linear combination of the elements of S. So it's still such a linear combination, and that's why it is closed under addition, the user vector space addition. Okay? And then, the law of composition is defined. You need what else? You need the identity. Identity is obviously there, because if you put all of these CIs to be 0, you get a 0 element of the vector space. Okay? So 0 is there. Additive inverse, instead of this C1 to Cn, put minus C1 to minus Cn. Okay. You get the negative of this, I mean, whatever that means. You get the additive inverse of this. So inverse is there. What else was right there? Yeah? Commutative? No, not commutativity, but associativity. Right? That is, if you add two of these elements, so if you take three such linear combinations, associativity is kind of obvious here. If you take three such linear combinations, you can add any of them first. Exactly. So abelian group is, well, commutativity is given to you. I mean, the operation itself is commutative. It's a choice, right? So we are done with the verification of the first step. About the next one, if you multiply such an element, such a linear combination with an element of f, all the coefficients change to something else, but they're still elements of f. Take an arbitrary a, multiply this with a, this entire linear combination with a. So this is a c1 v1 plus a c2 v2 dot order a cn vn. Okay. Is it alright? So both are satisfied, and that's why we can call span S a subspace of V. So actually we already proved this. That is the proof is kind of just straightforward verification of the definition. So proof is verification of the definition. Okay, but nevertheless I am writing it down like this here. When you by the way, today the things are being prepared by Anuvansh. Anuvansh is there. It's Anuvansh and Praveen, Piyush, Bhargav, Asumi, yeah, and who else was there? All five. Okay. So yeah, please take the notes till now. I mean, when you finish it, you can send it to Rohan. Rohan is still your group mentor. And Rohan, also please send the send the other two things. I mean, the previous two notes with comments. The first one you have already done. I see. Then send me the final version, what you have received from the group. And the next one, which is under review, please send them your comments. So I'm just writing this definition out like here. What? This is not an ordered pair. Here we took S to be an ordered finite set, but there the definition is more general. We are taking any arbitrary set. It is set with no other properties except it's a subset of it. Ordered set. Well, here we mean that the order is preserved. So that means you are not allowed to replace V1 with V2. But nevertheless, this is, well, we will soon we will talk about something else, and there the order will not be important. But here the order is important because you see, so consider R2, okay, and suppose we take an ordered pair. Well, in R2 it is, if we take linear independence, then it's always the same full R2. So maybe we take R3, okay, and then we take two vectors. For example, well, it's a linear. We're taking all linear combinations, right? And it is, these are additive. So it means that if we take an ordered linear combination like of V1, V2 to Vn, and then if we replace swap V2 and V1, we still get the same span, don't we? It's because suppose we take the linear combination of this and this, and then we are calling this V1 and V2, okay? And then we replace and call this V2, call this V1. We are getting still all the linear combinations from
But when we want to prove that, like say it's unique or something, then it will be important, right?
Yeah, actually when we define a basis,
yes,
this will be important. But for defining span, we could certainly do without ordered pairs. Okay. it's just standard to start with the ordered set of vectors, but nevertheless, I mean, if instead of ordered pairs, if you would have taken these ones and not an ordered set but any set, then this still works. I mean, all the linear combinations of these are giving you the same thing.
Sir,
Yes.
when we are writing, initially we are writing a finite order set. In that case, can we write that S is a subset of V? I mean, V is a set of all the random vectors in a space.
Okay, so then do not take an ordered set, just take V1 to Vn, an arbitrary set. So when you are taking an ordered set, since V is not a tuple of ordered set, what you have to say is that all these V1 to Vn are elements of V, and we are taking an ordered set of them, positive, ordered tuple of them.
So the order of the vectors might not matter, but the order of the coefficients, like
Indeed.
will
Sure,
matter.
sure. It will.
It's 3i cap plus 4j cap.
Nevertheless, if you are considering all of the linear combinations, then it is not going to matter. I mean, for defining a span, it doesn't matter. So once you have defined span, well, we have also showed that it is a subspace of V, and then as a corollary, we can immediately write this, that if you have a subspace of V, so the corollary to the first claim is that if you have W, a subspace of V, and if S is some set in V, so S is some set in W, some subset, then that will imply span of S. Now that span of S is also a subset of a subspace of V, right? So, and all these elements were in W. W is closed under addition and also scalar multiplication. So we can say that this is a subspace of W. Right? Because W is a subspace. S is an arbitrary subset. Now we are taking the span of that subset. It is itself a subspace. Okay. And note that since these are elements of W, all their linear combinations would be in W as well. Well, if you add two of them, they are there. If you multiply them with some elements of F, it's still there. Okay. Now you can take, if you multiply with them something with some scalar, add them, you are getting the linear combinations. Okay. So you could get all the linear combinations of the elements of S in W. W is still closed. So that means this would be a subspace of W. Right? What does that imply? Span is actually the intersection. I mean, it sits in all the subspaces that contains S. Right? So this is basically the intersection of all the subspaces of W. So the subspace of V that contains S. So you still need a little more argument to show that this is indeed this. So I asked the batch who is responsible for today's class to write it clearly down. Right, both sides. We show that this is inside this. How is the other thing?
Sir,
This is a small homework for you.
so how is S a subset of W? Because like S is basically the elements of S.
S is a subset of W. And now we are talking about span of S. So W is a subspace of V. Again, I am writing it clearly.
So by that you mean all the Vi are in W, right?
Yes. So you are taking the intersection over all the subsets W, which are containing this set S. if it is difficult, I mean, if it is the same W that is making a problem, call it W prime. Okay? So you are considering all such subsets of V which are containing S, and then you are taking the intersection of them. That would give you the span of S. Yes, yeah. W prime is a subspace of V. In other words, I mean, what I want to write here is that span of S is the smallest subspace that contains S. So, I mean, there is an analogy. I mean, while we defined GCD, what we saw that some number, I mean, if there is a divisor of the number which is dividing all the other divisors, then that is, I mean, except one, of course, then this is, well, one could, I mean, if you have a pair of numbers, and one could also be their GCD. Sure. So you're taking the highest number which is dividing all these numbers, and you are that you are calling the greatest common divisor. Here you are taking the largest subset which is inside all these subsets, and you are calling the span of S. Okay? So you could define span of S in a different way. I mean, just in this manner, forgetting about all the linear combinations. Take all the subspaces that contains that is containing this set S. Take the intersection, and you will end up with the same span.
But how do we show this definition implies the original definition?
Yes, I said that's a small homework for the other, because we saw that this equation is clear.
Yeah, like the original definition implies this.
Yes, but the reverse should also be clear, because I mean, well, it's a small hint that is note that S is inside W prime, right? What are the properties of these ones? It should be closed under addition. It's an abelian group. It's closed under multiplication. So all you have to show is that, using those two definitions, that if you take any elements of S, any linear combination, those belongs to all these subspaces which contains S, and you are done, right? So this we have already seen. This is also sort of trivial. Yes, Anush, is it fine?
So what you say span of S is the largest subset?
Is the largest subset that contains S. Oh, not largest, excuse me. The smallest subset that contains S. Wait a minute. Subset, not subset, subspace. So this implies span of S is the smallest subspace of V which contains because it is sitting in the intersection of all of them, you see. Yeah, it is sitting in the intersection of all of this. All right. So I mean the largest. I mean this was the smallest subspace which contains S, and I mean while we drew the analogy with the GCD, then only we mentioned that there is, I mean, the largest came there. So suppose we have a set of numbers A, B, C, and we list down all their divisors, and then we take the greatest one among them, which is sitting inside all the sets. So this is the set of divisors of A, divisors of B, divisors of C. We intersect them and take the largest one sitting. So that was just to give you the analogy, nothing else. Now we define what is a linear combination. Not linear combination, linear relation. Linear combination we have already defined, sorry. So linear relation is quite easy to understand. You are given a set of vectors, again a finite set of vectors, quantity to Vn. So given a finite set of vectors C1 .Vn if there exists C1 .Cn in F such that C1 V1 plus Cn Vn is equal to 0, where not all Ci's are equal to 0, then we call this a linear relation. Wait a minute, I can write here. So it's a linear combination which is equal to 0. We will call that a linear relation. Then we call this one, call this, give this equation a name, say star, a linear relation between V1 Vn. So if some linear combination is 0, then we call that to be a linear relation among the given set of vectors. Okay? Yeah. So then comes the notion of linear independence. A linearly independent set a set V1 Vn of vectors, we could still work with this bracket. So if such a set of these vectors in V is such that there doesn't exist any linear relation among V1, V2 to Vn, then we call this set a linearly independent set. Okay, so what does it mean to have no linear relations? Exactly. So if there exists, if you write it down, write such a thing down, then all the coefficients are to 0, because otherwise it is having a linear relation. So that implies, can I wipe the first part of this board? Or maybe that one, right? That one was the oldest one. So that implies, well, this is if and only if there exists C1 Cn in F such that C1 V1 plus Cn Vn equal to 0, that implies C1 equal to C2 equal to everything has to be 0. So if there exists such a relation among them, then that implies that all the coefficients are equal. So that's the meaning of linear independence among a set of vectors. And such a set is called a linearly independent set. A set of linearly independent vectors. So linearly independent set is just such a set of vectors which are linearly independent. Or a finite set of vectors now we prove a proposition about that. That is, suppose you are given a linearly independent set. For example, here. At first, we give some examples of linearly independent set, right? So, for example, we considered this was a picture that we drew earlier. We took one element here, say 1, 0 here, and well, this is three-dimensional space. So say 1, 0, 0, and this should be 0, 1, 0. Okay, and then suppose we are having a linear combination of them. How does the linear combinations of them look like?
C1 into 1, 0.
Yes, C1 into 1, 0, 0, say, plus C2 into 0, 1, 0. Okay? And that is basically just C1, C2, 0. Note that such a thing, for such a thing to be equal to 0, that is all the elements is 0, that would be simply just this one is 0, and so I mean both C1 and C2 has to be 0, otherwise it is, so if, what I want to say is that if this is equal to the 0 vector, that would be if and only if both C1 and C2 are 0. Okay. So yeah.
A doubt.
Yes.
For the linear combination to apply the taller zero, you cannot mention that V1 and V2 all are linearly independent.
Well, note that this is, so here you mean that this is
Like if I go from that statement to the one that C1 and all are zero,
yes.
should I not already know that V1 and all
Yes,
are
this is where we are coming from. This and this was a continuation after this. So that if and only if line is coming after this definition of linearly independent sets. So here we say that a set is linearly independent. We want to do the Bn if and only if there exists. I mean, if and only for any such linear relations, we have all this equal to 0. Okay. So this is of course a continuation after that, and this is this and that are not linearly independent. Okay. So this is a continuation. Yeah. So such a thing, I mean, not only here, if you take a pair of, well, if you take, say, I mean, give me a 3 cross 3 or 3 cross 3 invertible matrix. Any invertible matrix, please. Well, identity is a trivial thing. Well, we can just add something on identity, right? We can make it an upper diagonal matrix. Upper triangular matrix. So 1, 1, 1, and say 1 here, 1 here. Consider this matrix. And then you know something about this already. That is, if you take the determinant, it's 1. It's non-zero. Right? So now suppose you take a linear combination of these columns. What it should mean? That is, call this first column V. Okay. So take the columns of this. Columns of this matrix A. Okay. So V1 is the first column. V2 is the second column. And V3 is the third column. Now, what does it mean to take a linear combination of this V1, V2, V3? Yes, right. C1, V1 plus C2, V2 plus C3, V3. This is a linear combination of these rows of this matrix where C1 to C1, C2, C3 are elements of the field, underlying field, say R or C, whatever field you take. Okay? Actually, you could take an arbitrary field here because these are just ones and zeros. Okay? So this one is nothing but, well, if you call this C1, C2, C3, this vector, if you call this as X, define X to be this one, C1, C2, C3. So what is this thing equal to? This is nothing but A times X, right? That matrix times X, X is this one. C1, C2, C3. So Ax is giving you the linear combination of the columns of the matrix, right? So note that now such a linear relation would amount to, I need to write it here. Can I what's the definition of X? Have you put it down already? So note that, or we can write it X somewhere here maybe.
So wouldn't it be rows of A instead of columns?
Ah, right. But it is still they're independent, right? Because it is, well, that determinant is non-zero. Right. Wait a minute. This is, thank you. So this is, wait a minute. Why it is rows? The column is fine, right? You are multiplying by the rows, but nevertheless, the first one, C1 is multiplied always with the elements of the first column.
I think I've
See?
forgotten.
Yeah. Okay, so note that now this is equal to 0. That means this is equal to 0. Right? Now note that such a thing exists, such a linear relation exists if this has a solution, this has a non-trivial solution. Right? Well, 0 is always a solution. Dikshit, please wake up. So, yeah. X, so such a thing is equal to 0 if and only if Ax is equal to 0 has a solution. Okay? So this is equal to 0 if and only if, well, for some C1, C2, C3, if and only if these some C1, C2, C3 which are not equal to 0, not all of them equal to 0, if and only if this has a non-trivial solution. Alright? And now we talked about something which we in the past classes, not in the on day 1, but in the intro or a little bit after that. So if we take this matrix A, if you take its determinant, that is going to be 1, right? That means this is invertible. Okay? So if you multiply with its inverse from the left, you are getting x equal to 0. Right? In other words, if you take an invertible matrix, its columns are giving you a set which is linearly independent. Right? So V1, V2, V3 here is called, I mean they're making a set which is linearly independent, because if there exists such a linear combination which is equal to 0, that would mean that this vector, there will be a solution, a non-trivial solution to this, which doesn't exist. Is this point clear to all of you? Otherwise, please ask.
If they're linearly independent,
Yes.
Then there will exist a non-trivial. There will not exist a non-trivial.
Right.
So A has to be invertible.
Exactly. Now suppose, yeah. Yes. What? Didn't you prove this already?
We need to write it formally, but
Exactly. We need to just write it formally, but nevertheless, isn't the logic clear to you? Again, Srinivas, where are you start?
No, sir. I'm just asking, do we need to prove this?
What?
That columns are linearly independent.
Well, you are not in the class responsible for today's writing, right? Okay, but nevertheless, I mean, if you are just I mean in the exam or somewhere, suppose you're faced with this, you can just say that its determinant is non-zero, that matrix is invertible, so the columns will be linearly independent. Just that.
also would work.
But
for
nevertheless,
rows.
today's class, I mean, who are noting down today's class, please write it down clearly.
So this would work for rows also, no?
Exactly. Yeah. Instead of you taking
Yeah, you
A is
take
equal to 0, you will take transpose of this.
Then it will be XA is equal to.
Yes, then if you take the transpose, it is A transpose X equal to 0. That's also fine. So now the thing was that if you, instead of V1, V2, V3, if you just put another arbitrary vector here, so what will be that set? So will that be, I mean, can you make a set of such V1, V2, V3 and some arbitrary 3 cross 1 vector which is still linearly independent. Yeah, so I'm writing it down here. So we just saw that we saw that if A is invertible, then the columns of A are linearly independent. Now suppose you take this set V1, V2, V3, okay? And you want to put another vector here. So V1 is the first column of A. We are still continuing that notation. V1 is the first column of A, second column, and this is the third column. And here we are trying to adjoin. Well, the next proposition would be on that. So this is an example which foregoes the which is an example which demonstrates the next proposition. So we are trying to put here some vector V4 such that this set still remains linearly independent. Is that possible? So can we include some vector V4 here such that well, all these are in R3. R3 is our base vector space. So such that, but as we said, the entries are 1 and 0. So you instead of R3, you could take any F3, any field, okay? Such that this new set, V1, V2, V3, V4 remains linearly independent.
If it's not a linear combination.
So that's the definition, right? That if it is not a linear combination of all of them. Now, is that possible?
No.
Why not?
It is possible.
Is it possible?
It is intuitively possible. If we take like two vectors, I cap and j
Okay,
cap.
then give me a vector which we could add there.
Acha, and read them.
Yes.
Yeah. 4 by 4.
So
These the basis.
is a question here to all of you. All you are trying to put another column here and asking whether this would still be linearly independent. This set of all columns. 0 is not a. By the way, as when we define linear independence, thank you for saying this. Oh, what's your name again? Or thanks Orko for saying this thing, because when we are defining linear independence, you need to be clear about two things. One is that in the set, no vectors could be repeated, because if you repeat two vectors in that set, so V1, V2 to Vn, say you take this set, and then in that, suppose you are taking the V2 and V, so you cannot do this if you are saying that this is a subset of V. But if you are picking them one at a time and saying that each of them is an element of V, and then we are taking some ordered set such that each of the elements are elements of V, you are still allowed to take a repetition of two vectors, right? Now, can you take a repetition of a vector in a linearly independent set? Why not? Because there is a trivial linear relation, V minus V, V1 minus V1, so V1 is repeated. V1 is repeated at V2, so V1 and V2 are the same vector. That would mean that V1 minus V2 is equal to 0. That's a linear relation, right? Is this clear? That is, you are not allowed to repeat any vector in an ordered pair for, if you're considering a linearly independent set. Is it alright?
I was not saying, I was saying that if you want to
Okay.
add another
Yeah, I'm
column,
come to that. And then again, in a linearly independent set, can there be a zero vector? Why not?
Because 0 as a coefficient
Exactly. You can take the linearly independent set as just a single vector. If that vector is 0, then you multiply it with any element from any coefficient from the field. You are still getting 0, right? That's a trivial linear relation. So that's why you are not allowed to take zeros in a linearly independent set, and you are not allowed to take any repetition of any vectors. Okay, so 0, 0, 0 is not allowed. Anything else? Yeah. You want to say 1, 1, 1? Normally? Yes, and you?
So if we add these four, then it will be linear independent. So we have C1 V1 plus C2 V2 plus C3 V3 plus C4 V4 equals to 0.
Yes.
Then C1 V1 C2 V2 C3 V3 is 0.
Yes.
Then C4 V4 is have to be 0. C4 cannot be 0.
Again, why? I mean, if you are having C1 V1 plus C2 V2 plus plus C4 V4 equal to 0.
So because V1 V2 is linear independent.
V1 V2 is linearly independent, right? But you are having a fourth vector here, right? So you cannot say that these three coefficients will be 0. Okay. So Ratnadeep? Yeah, again, what's his name? Kohli. Thank you, Kohli. But this, I mean, you see the point, right? If you write it down, we cannot say that these three are equal to 0. It's a linear independence is a statement of about the entire set. Alright, and now Robin said that perhaps this will work at 1, 1, 1. Yes, this might work. Do you think so? If you think so, why? If you don't, why not? Anybody? Yes.
But if we add any fourth column vector, then the matrix will not be invertible.
Well, we are talking about now a 4 cross 3. What do you mean by that? So now what we are saying is that instead of calling it V1, I mean, we are calling it still V1, V2, V3, and this one is now or V4, as Dr. said. So the question is that can such a thing still be linearly independent? I mean, can all this V1, V2, V3, V4 be linearly independent vectors? Why not?
Since A is invertible, it means we can like get all the combination of vectors present in that R3 from the combination of those three. So definitely we can get one.
So all you wanted to say, I guess, is that this thing Ax equal to 0, since we have the only 0 solution, how do we get that? Because A is invertible. Multiplied by A inverse and we got 0 as the only solution, right? Now instead of 0, put 1, 1, 1 there. Multiply by A inverse. You get some elements there. Alright? Or you can also think like this. That is, these are, how many unknowns are there? Now 4 unknowns, right? Okay? And there are, so 4 unknowns, 3 equations. So you must have done this in the previous class. If you put it there, if you consider the 4 cross 3 matrix, if you do the row reduction, then you will have pivots. You can have pivot only in 3 columns, so 3 rows at most, right? So this will always have a non-trivial solution. Okay? So you can a non-trivial solution would mean that this equal to 0 will have. I mean, there should be something. At least one of them is not equal to 0, and you are still getting a linear combination which is 0. So you can come to this in both ways, either by row reduction or just by the invertibility of it. In fact, even if A was not invertible, then, well, even if A is non-invertible, that would already give a linear combination, I mean linear relation between V1, V2, V3. So that means if A is non-invertible, if A is singular, that would mean that there exists some x which is non-zero for which you are having such a thing. So even V1, V2, V3 is not linearly independent. Forget about adding a V4 with that. I'm making it a linearly independent set. Because no subset of a linearly independent set is allowed to be, no subset of a linearly dependent set is allowed to be, yeah, well, let me check.
No.
The opposite thing. Okay? So we are asking that V1, V2 to V4 to be linearly independent. Now, V1, V2, V3 cannot be linearly dependent because that would give.
So they could reduce that into a smaller limit.
Exactly. Yeah. So let me write these three things down. Can I wipe this part out? Thank you. So at first, what Orko asked, that is, and what we told while answering him, no repetitions in a linearly independent set to zero, the zero vector can be an element of a linearly independent set and thirdly, no subset of a linearly independent set can be linearly dependent. Okay?
So,
Yeah.
so if we had the opposite case of that example, suppose we were given like a set of linearly dependent vectors.
All right.
Could we add any vector to it so that it could become linearly independent?
No, because we said that no subset of a linearly independent set could be linearly dependent. Now, if you add,
Yes, if I add this with algebra.
so that would contradict this last thing that we just said. Because you see why? I mean, having a linear relation among a smaller subset means that having a linear relation among the bigger subset. Put zeros in the other coefficients.
Yeah, that's what I was thinking.
So the next thing would be when we could add such a thing. I mean, when suppose you got given a linearly independent set beyond V2 V3, now we want to add a thing V4 with that, and we want still a linearly independent set. When is that possible? So it's a very small proposition, but it's a quite nice one. We'll finish the class soon after that. So I was working this part. Yes.
When the first three vectors cannot span the whole of the vector space, then we can add one.
Yes, I'm just going to write down the proposition. When we can add one and when we cannot add one. So let L equal to V1 to Vn be a set of or a linearly independent set. And suppose we add one on V2. So let V in some arbitrary vector. Okay. Alright, now we're taking an ordered set. Well, actually, as we mentioned, we can always also work at least till linear independence and spanning. We can certainly work with non-ordered. I mean, we can replace these ones with curly brackets. Till now, when we are not talking about basis vectors. So yeah, it is still possible. Instead of taking an ordered set, you can take this one. This in fact remove already the first thing, that is it's a set. In a set, no revolutions are allowed. Right? So now we are considering something else, call it L prime, and this would be L. We are considering LV. I mean this one, and this would actually, I mean, if you use the computers, I mean the brackets as you use in programming or computer science, that would mean that this is like V1 to Vn, but so this in computer science you think that this is V1 to Vn and V, but in our notation this is just a notation for augmentation. Okay, actually this is a standard notation, this using the ordered set. So pardons for that, but let's work just with ordered set, and this would mean for us this LV that we are adjoining this with this. So excuse me. this is an augmented set. You want to do Vn and then we are putting a V there. Okay? And then the question is that, well, not question, it's a proposition. Okay, so L prime is independent, is still linearly independent. It's given that L is linearly independent. Okay, independent if and only if V is not in the span of L. Okay. So yeah. Well, the proof of this we could do it in the next class. We could try. The next class is tomorrow, right? So we finish the proof tomorrow. Tomorrow there is no stats probability stat class. Instead of that, we have the linear. And the proof is rather simple. So you may also try by yourself because we will run out of time.